Okay, we still have a minute or so, but uh, if you haven't ordered your Hexaware, please make sure to do it. We'll hand out the first assignment, and also we're really hoping that next discussion section can make use of it. So I think a lot of you, I saw that it's expected to arrive by the end of the week, but just make sure of that. I also posted last week's lecture recordings. Um, so they're on the YouTube channel. Um, any other questions before I start? There's a YouTube channel, so if you go on to Piazza, you would see on the resources, general resources, there is a link to YouTube recordings, and you just go on to that channel and the videos are there. Okay, and for each one of the 2 days, there are two parts to it. So it's kind of file name is obvious. It's just a date, and then you'll see part one, part two, like that. Okay, and I think you also recorded a discussion section. You're still trying to fix it. Okay, well, okay, it's best effort as we kind of said. So unfortunately, it's kind of not being done professionally by the school, but I think the lecture videos are pretty decent. Okay, so want to recap some of the things that we did last time. So this is okay. So recap from last time. Um, so I think the main thing that we covered last time was uh, how to the energy related considerations, and first thing that we had looked at was the three different ways, very broadly, that we can look at how energy slash power can be managed. So one of them was simply shutdown. That is, unused parts of the system we shut down, and kind of one of the issues that we face there is that there is cost associated with putting hardware to sleep and waking it up. So there is transition cost, and so that means that you can't be very aggressive, like, oh, the moment the system is idle, let's shut it down, because if the system is going to be needed very quickly again, then you are paying extra time and energy, and that's going to affect both performance and energy efficiency. So that was one issue. The second issue, the second aspect was that I talked about how systems themselves, the hardware itself, provides multiple modes, and we had used the processor, which is on Hexaware, as an example, that how it had a whole bunch of states. And generally speaking, as you might expect, the deeper the system goes into sleep, so to say, that is more reduced functionality, then of course the more benefit you get in terms of energy, but you also pay the penalty of it takes longer to come out of it. Or and usually when you go into a lower power mode, so lower power typically implies reduced functionality. It also implies increased time latency to come in and out. And there is also possible state preservation, okay, which is, if in the most extreme case, if you truly power down the system, effectively you get zero energy, but then you lose all the state unless you happen to have some sort of flash or some persistent memory, and of course it takes more energy. So there are all these kind of implications, very platform specific, and one of the sort of the running thread through the lecture last time was, you should really become familiar with the platform so that you can fully exploit these capabilities. Okay, so that was shutdown. Anyone remembers what were the other two mechanisms? Frequency scaling, so slow down, right? So, and the third one was frequency plus voltage. Okay, and the deal was that frequency scaling alone reduces power. So this thing reduces power, but not energy. Energy for a given function. And the reason was that if I scale the frequency, then the time taken increases proportionately, and energy is power times time, and therefore we end up back where we started. But voltage gives us additional knob, and the idea was that voltage has some relationship with speed, namely higher the voltage, higher the speed, and very crudely you can say proportional. That's not true, but let's say they are. And we had looked at this formula that P is proportional to V square F, and therefore that in effect translates into that power is proportional to either, you can say roughly speaking, cube of frequency or cube of voltage. And so I can play this game. So if you reduce the frequency, then you can afford to have a lower speed hardware because you're running it at a lower speed, and therefore you also reduce the voltage. So you kind of try to combine it together. Now the complication that I pointed out was that usually processors give you a way to change the frequency very easily. Almost all processors you would find have some sort of a register where you can scale the frequency. So the incoming frequency into the clock into the processor, you can multiply it up and down, and then you actually run the logic of the processor using that modified or scaled frequency. But voltage is very rarely on chip. Okay, um, it's it's not the case. It's never. There are processors out there where the voltage regulator, the thing which changes voltage, is on the chip, but usually you will find it on the board. It basically means that the chip designer, the processor designer, really can't give you any guidance on that. This is really when you decide at board level. Okay, so those were the energy considerations. Then I had talked about energy proportionality. And the idea and the issue in energy proportionality was that it's very hard to design hardware whose power versus speed or performance, right? Let's say speed looks like this. It's very hard to design that, okay, or whatever, some slope, okay. That is, ideally you want, if I'm not running, should consume zero power, and then as I get better and better performance, it's proportionately higher power. But it's hard to get this. And the reason simply is, and this is a set of an example we had seen, that big processors tend to be very efficient at doing large amount of computation. But just because they are big, when I slow them down, then I'm in the inefficient regime. And the analogy I had given was, imagine you have a car which is optimized for high speed. Then if you are doing city driving, then the powerful engine is just burning gas. On the other hand, little processors, 8-bit architecture, 16-bit architecture, so kind of just simpler architectures, not very pipeline, fewer execution units, they tend to be lower power, very rapid to go in and out of sleep modes. Since they have fewer transistors, they're very efficient at sleeping. But when it comes to bulk computation, let's say want them to do some heavy-duty computational tasks, then they begin to lose out. So so it's very hard to kind of achieve energy proportionality there, because if I take a little guy, it might be fine here, but then this side it may begin to max out very rapidly.
What is the S stand for this?
Speed. Yeah. Power speed. And I'm using these terms loosely. I mean, speed may mean many different things, but kind of some measure of performance. So that had led to the idea that we can fake energy proportionality by combining things. And there were two approaches I had mentioned. One I had gone in more detail, which was this big dot little concept, where the idea is I take multiple processors which are optimized for different parts of this power speed regime, and then I put them together, and then through some magic of software, I arrange that the right one is being activated. So if I have to do a lot of work, the big processor is activated, and if I have to do little stuff, I'm going to move to the little one, and I may have more than two. But commercially, you will see big dot littles very commonly available in processors where they pair up a simple processor and a big processor with identical instruction set architecture. So the same program can run on both places. Their microarchitecture is different, and I've given the example of ARM because ARM with the same instruction set, same 32-bit instruction set with the vastly different implementations which are out there. They differ in things like how much cache is there, they differ in how deeply pipelined the processor is, how many execution it has, does it do speculative processing or out of order execution, where you begin to look farther out and say, okay, maybe I can execute an instruction even though it is farther down in my program because all the data that it needs is ready. So these are concepts you'll see in some computer architecture course later on. But very crudely speaking, complicated architectures and simpler architectures, but you do want to make sure that that the program should be able to run on these places. And the specific example I've given was A7 and A15, but there are other similar things kind of out there. And the second approach, which I had not gone into a whole lot of depth, was to have a large number of processors or computers, and then activate some subset. Okay, and the example out here was like imagine like a data center or a rack of computers where I have a whole bunch of computers, except that I power up some fraction of them based upon how much my workload is. And in all these cases, as a common thread you would see in all of these things is that it's very important to understand your workload, right? I mean, because whether it's a decision to shut down or whether it's a decision to scale frequency or voltage, or whether to move from big to little or little to big, or how many computers should be activated, they all have a measure of predicting the workload because there is a cost associated with transitioning, and so you are always constantly in this game of like, what's my policy? Should I turn on some one processor? Should I put the workload to a big guy just because I'm seeing a spike in workload? All of these things, you're making a guess about the future, and if you're wrong, of course, you're going to pay a penalty. So people come up with all sort of carefully crafted rules. They try to see how your application is actually running. Machine learning algorithms, these kind of things are very fashionable nowadays. And then there is some little corner of your processor chip or board where you usually have something called a power management chip or power management controller, which does all of this management. So it's the OS working in concert with the hardware which makes all this energy magic kind of work. So I have a whole graduate course which kind of focuses on energy because it's a pretty deep topic, such as programming language, compilers, operating systems, and of course hardware and all sort of things, and not just the CPU, but also network interfaces and memory, and also it's a complicated topic in itself. What we will do in this course later on is that we'll go a little bit deeper into the specific processor so that you can play with these power management states. But one of the things I would like you to urge is that take a look at, I think I said last time also, take a look at the data sheet and particularly the power management section where it describes different states that exist for this particular processor. This is obviously a more abstract view. Yeah. Any questions on this? Okay, so the other topic which we had started on was I/O, and I sort of just want to recap a few of the things that we've done. We'll dive deeper today. So besides in embedded systems, besides kind of constraints like time and energy, the other thing which is a very key attribute is they interact with the outside world. They interact with the outside world uh, to either measure it or to affect its state, like through some sort of actuator, a robot arm doing something or a motor moving. And then also they talk to other things, other computers over a network, right? So broadly, you have communication and I/O and all these kind of things which get lumped under the same category. I kind of make this crude distinction, as I mentioned last time, that by I/O I'll generally refer to talking to peripherals, components, physical world, kind of like a nearby kind of thing. And then communication is when I'm trying to talk to another computer, perhaps even quite a bit distinct. Sometimes these distinctions are not that sharp. Like for example, I may have a peripheral which in turn may have a CPU, and therefore when I'm talking to it, it kind of seems like communication. But let's say crudely stick with this for a moment. But in particular, the standards which are out there and the technologies which are there, it kind of fall into these two clusters with some overlap. And so the focus for now is going to be kinds of technologies that are available for this left-hand side of things. So I talked about the Hexaware itself and that how it has a whole bunch of sensors on that little board. These are all individual chips that you see, CQ, and so forth. And then they're talking to the processor, the MCU, over some sort of a bus. Some sort of interconnect. So it's connected to the pins out here. And then up on the top, there is a flash memory. You will see it says serial flash memory. Serial meaning that it's communicating with over some sort of a protocol where the bits are sent serially. And the reason is that unlike, let's say, an Intel processor, the MCUs typically do not have an address memory bus. Okay, so you cannot hook up parallel memory ports and all. You'll see that much of the communication happens serially. You also have a display, a vibration motor, so you haptic feedback. There is also some touch buttons out there, and then there is second processor, which is in the form of this BLE SoC. So BLE stands for Bluetooth Low Energy. SoC stands for System on Chip, and this chip in itself has a little processor in it, and its primary task is to do Bluetooth Low Energy communication. So it has a radio built in, and so that you can talk to like your phone or to other peripheral devices. And then you'll see on the left-hand side there is this whole battery charging stuff out there, and you also see that there is an expansion port on this, and at the bottom of that watch-like device there is a little connector which is an expansion port, and then the breakout board which exists. That expansion port connects there, and then it brings it out into a more comfortable form factor. So that's what this thing is. One of the other things you would find very useful as you go around, as you go further in this course, is to also read the data sheets of these things, just to understand what these sensors are, what do they do, what are they capable of. Okay, so at least read kind of page 1 of these. You can easily Google for these, but also actually if you go to the embed website, go on under hardware, you will see a Hexaware link, and then if you just follow that, you will see a page where they have given data sheets for all of these things. So it's very well organized on the main website itself. Okay, one thing that you notice is that kind of there's a diversity of these I/O devices, and the thing that matters to us really is that in what ways they differ. So first thing when it comes to talking to these I/O devices, obviously things like what kind of performance they can, data rate. Clearly, some of these devices like displays have much higher data rate, or a camera. On the other hand, I don't know, something like a mouse, for example, or a temperature sensor. These things don't need to have really high data rates. Then another aspect on the time side is latency. Some of these things do require tight latency. That is, you do want to make sure that when you ask the device to do something, it does it within a very short period of time. Otherwise, the impact. Like for example, again, if I'm displaying something on a display, excessive latency can be very problematic. Synchronization refers to that I want two devices to do something together. Like for example, if I have a speaker and a display and I'm sending the video image onto the display and the sound onto the speaker, I do want to make sure that lip sync is maintained, right? I mean, so there's going to be some requirement in terms of when the data is appearing out or when it is being sampled in reverse direction. So that's the synchronization. And then finally, how do you access these devices? Some of these devices offer an abstraction as if they're like a memory. You give it an address and you read an arbitrary location. So in that case, that would be random access. And then sequential is where it's kind of like a queue. I read, then next time I read it, the next thing, there's no address. So there are a variety of requirements. A very important thing which comes up in a lot of embedded systems is constraints on the pin count. If I want to connect a lot of devices, if I were to give each one of them dedicated pins, then my processor will bloat up. Now, one way you can handle more pins is to use fancy packaging. So some of you may have seen chips where the pins are at the bottom part. Okay, they're called, anyone knows what those sort of chips are called, where the pins that connect to the board are all in the bottom part of the chip. Okay, something you will find if you just Google called ball grid array. Let me see if I can. So if you see out here, what this is showing the bottom side of a chip, and it has basically this grid of pins there. So unlike normal PCBs where you see the pins are on the side, this is basically along the bottom, and then what you do is when you slap them on the board, there is a similar pattern on the board, and then somehow they manage to solder it. This gives you pretty high density, but these are pretty expensive things. So you can achieve high density packaging and high density pins, but they come at a cost. And even then, obviously, there are limits to what you can pull off. So pins tend to be a constraint. How much power you have to supply to these peripherals? Many a times, the peripheral receive the power from the processor itself. Can you give me an example of such peripherals? Mouse often have batteries, but sometimes they don't, so they come. Yeah, but you're right. USB device in general, right? USB and even HDMI, they're all designed for delivering power also, with some limits, right? I mean, and I mentioned that even Ethernet, there's something called power over Ethernet. So delivery of power to devices, to peripherals is something that there has been some worry about. And so now, when we talk to devices at an abstract level, there are kind of a few distinct functions that as a software designer, one will have to do. One is that these devices tend to have parameters, like for example, it might be the rate at which the sensor is sampling the thing, or maybe the rate at which the radio is sending out the data, or maybe number of bits it is using to represent things. There are also parameters you can imagine, the sensitivity of a sensor. So all of these kind of parameters, reading and writing, getting it set. Then transmitting and receiving data. Network, a radio receives a packet over the air, and it needs to hand it over to you, or you as a processor need to hand over a packet to the radio to transmit. And finally, enable and disable functions. Like for example, I might want to tell the radio go into a transmit mode or go into the receive mode. So those are all examples of the kind of functions that you might expect to do. So that raises a question: how does the software get the access to the I/O? So typically, these peripherals, if you want to look at data sheets, they will basically present themselves as some sort of a register or registers inside the peripheral, which the main processor can read or write. And one question comes up is then how should we expose it to the software? How should the processor access it? Now, at some abstract level, they seem like memories. That's what they are, the memory locations. Question becomes that are there differences in it? And towards the very end, last time I was talking about it, which is that there's a few key differences which do occur between standard memory, data program memory versus device registers. But a very key one is the following, that we are dealing with, in many cases, effects which are eventually onto the physical world. So once I do something to the physical world, I can't take it back. And likewise, when I'm writing to the physical world, when I want the device to do something like send a packet, I truly mean send the packet now. Whereas in case of a data memory, I can write to the data memory and it may just go and sit in the cache. And then later on, the hardware may decide lazily to write it. So, so we can't quite deal with the same deal with these things in the same manner. Then there are also implications about certain peripherals and all. I may want to do operations on them where if I have to share it with something, some other application, I may have bad things happening. Like I may change some value and then the other application comes and changes the value, and then that may result in kind of all sort of nasty things happening. So we need to make sure that the operation of the device is kind of protected. So what all of that leads to is a few considerations that make things. So firstly, usually I/O cannot be cached. Okay, if I'm writing to it, I want to write to it immediately. If I'm reading from it, don't give me a stale value from the cache. Go and fetch a new one. So can't cache. Timing matters. Okay, and this kind of relates to the whole issue of caching. That is, I may have tight timing constraints. Reading and writing can cause the hardware to do some function. So in standard memory, when I read or write, that's all that happens. It gives me the data value or it writes the data value. There's no side effect. Whereas in a, let's say in a radio, writing to a register may result in a packet going out over the air, or in a sensor, reading from a register may cause it to read a value, and so on. Can't undo the effect on physical world. If I got the robot arm to smash in the wall, I can't sort of undo it. And then sharing can be challenging. So these things do differ, and that begins to reflect that processors handle I/O differently. And there are two broad approaches that exist in commercial processors. One is that there are specialized I/O instructions as part of the instruction set of the processor, and Intel tends to use this. So if you look at the instruction set of Intel processors, there are in and out instructions which are meant to read and write to I/O ports. And what happens is that these particular instructions are made available only in that mode of the hardware where the operating system runs. So a sidetrack out here, processors. So what happened? Yeah. Processors often have something called modes. And the idea is that in different, so this is execution modes. And the idea is that in different modes, different, not all the instructions may be available. So, right, so for example, there are certain things which you want only the OS to be able to do. And so in the so-called privileged mode or the kernel mode or operating system mode, all the instructions are available. And then there might be a mode for users, and there only a subset of instructions might be available. I/O instructions tend to be an example of that we don't want normal programs to be messing with them. Now, having said that, not all processors have these kind of execution modes. Simpler processors don't make a distinction. Everything is just one mode. But if you're looking at like Intel's whatever, x86 processors and all, they have this hierarchy of modes. Like Intel calls it rings. So ring 0 in Intel processors refers to a very privileged mode. That's where the operating system is. And then they have ring 1, 2, 3, and then normally in operating system, ring 3 is where the applications run. And then in newer processors, there is a even more privileged mode, which is used to run so-called virtual machines. Virtual machines is where you can run kind of multiple fake computers on top of a single computer. Okay, and each one of them can be running their own operating systems. So hardware provides support for all of these things. I/O instructions tend to be more privileged because you want only operating system to be messing with these I/O devices. But simpler processors do not have these privileged modes, so you won't see that aspect out there. So for example, the processor that you have on Hexaware, it's not really designed for general purpose usage, and also it doesn't have a separate user mode versus kernel mode and all. Okay, it just has a single mode. But Raspberry Pi, there the processor is running Linux. It's designed for kind of a multi-user environment. There it has multiple modes, except it has an ARM processor, not an Intel processor, but it does have that. So simpler processors don't tend to have privileged versus non-privileged mode. Whereas processors meant for general purpose, more general purpose usage tend to. So specialized I/O instructions, and in this case, what's happening conceptually is as if my memory resides in has its own set of addresses, and I/O ports reside in a separate address space. They are two separate things. I/O instructions may refer to my I/O port number 10, whereas memory instructions refer to some memory address, and they're just two separate. I cannot take a data structure in my program and map it to I/O ports because it's just separate. The second one, as you might gather from it, is to really think of the whole thing as one address space. So in that case, there's nothing special about I/O. There are just certain addresses in my memory address space. So the same instructions we use to read and write to addresses, memory addresses, are also what I use to read and write to the I/O. It's just that we set aside some part of the address space for this purpose, and that may often depend upon the operating system, board designer, and things like that. So accessing devices in the second case is just like accessing memory, which is kind of nice and clean because I can use just the standard way of programming things. I don't have to worry about this additional set of instructions. But then the issue comes up, how do I achieve all these issues? How do I tell the hardware don't cache it? How do I tell it all these properties? So it turns out that processors typically allow you to give special attributes to different areas of the memory. So you can tell the processor that a certain range of addresses, I don't want it to be cached. That is, whenever I'm reading or writing from it, bypass the cache, for example. So ARM processors tend to be in this category. So this is where ARM processors are. Okay, they don't make a distinction of there's no I/O port, there's no special instruction for I/O. It's all part of the same. You can transfer from a register in the CPU to a memory address and vice versa, and you make the fact that it is I/O, you make that happen by dealing with the mechanisms that the processor allows you to have, so that there is no cache and there is no and the appropriate protection. Now, our particular processor doesn't even have cache, so you don't have to worry about it. Remember, these are MCUs. All the memory is sitting on chip. So usually you have caches only when you have to go on and off chip. If memory is on chip, then it's already pretty close to the processor. There is no need to have a cache. So we don't even face that issue out there, the caching issue. So the advantage of this is that, let's say I have some device, let's say a radio, which offers me a bunch of registers. I can map those set of registers into a C or C++ data structure, and then just read and write to it as if I might read and write any other data structure in memory, except that in this case, reading and writing to those locations will have the side effect of working with my radio. So gives a cleaner way of programming these devices. So again, since x86 is not widely used in embedded systems, more likely than not, when you're working with these things, you're going to encounter this. This model is by far the more common one. Almost all other processor families tend to use this, and also the tiny processors. So this memory mapped I/O is kind of the more common. I mean, it happens to be in this case, but no. Although you could argue that, yeah, I mean, maybe having two separate things is more complicated, but the I/O instructions and the memory instructions even here were reasonably simple. So I don't think that was a thing, but it does happen that risks as part of just keeping things simple went in this direction. It does make compiler's life a lot easier because compiler doesn't need to know about this separate set of things. So just overall, a lot easier to work in this kind of setting. Intel unfortunately cannot get out of this because well, they have to maintain backward compatibility. Okay, so which one is better? Thoughts? Okay, so tell me the trade-offs. When is this one better? Okay, so possibly more security. What else? I guess I told you the pros of this one, right? A cleaner programming abstraction and all kind of thing. Let's look at, yeah, I don't have list. Okay. So what else can you think of? Yeah, it can work both ways, right? I mean, if I have some I/O devices which have a huge amount of memory, like let's say a camera or a frame buffer and all, then we actually run into problems. So I guess generally speaking, this is just viewed plainly better. I think there is nothing that you can do out here that you can't out here, other than the fact that if you do need a sort of ability in the processor to enable disable caching and all here, the hardware designer can just takes care of it for you. So cameras often have like a large image, and that means you need a large address space. Whereas IO ports tend to have pretty small, like they may have 1,000 ports or 100 ports, whereas a single image itself would be millions of addresses. Whereas you don't run into this problem over here. I can take my entire image and just map it into address space because the address space itself is 64 bytes. But on the other hand, you do have the more responsibility out here to make sure that the semantics for caching and all are done right. Now, a question naturally arises: how do I tell the compiler that forcibly go and read the location? Okay, bypass the cache. Okay, or don't optimize it away. One of the problems that we often face also is the following. Let's say I say a equal to read from address whatever 0x10, let's say that's an address, and then again I say b equal to read from the same address. A smart compiler will say, aha, you are doing the same thing, reading the same thing again, so it will just scratch out this one and then simply set equal to a, right? That's mathematically equivalent. But obviously, with I/O devices, that's not correct. You do want to tell the compiler, don't optimize this. So there's a way in programming languages like C and C++ to tell the compiler that this variable is kind of mapped to hardware. When I say read it, do go and read it. Anyone knows what? Okay. So there's a keyword in this thing called volatile. So if I say volatile int x in, let's say, C++ or C, then this volatile means that this variable is mapped to an address where when I say read x or do something to x, you better go and read it. Okay. So volatile is additional thing, part of our C and C++ language. And this is something which in standard programming you'll probably not see much unless you happen to write programs which perhaps talk to another thread, like two threads talking to each other. But generally you don't see it. But in hardware, where you're interacting with hardware, this is going to be quite common. So now let's walk through different types of ways in which MCUs interact or provide you I/O. So the first one, which is kind of very common, is simply called general purpose I/O. And these are pins on the MCUs, which can be read and written by the software, and they're digital pins. In the sense, each pin basically can have a state of 1 or 0. If it's an output pin, and if it's an input pin, it can read a voltage level and classify it as 1 or 0. Very lightweight operations, because there would be basically these pins will be mapped to some register in the MCU, and then you read it and you get some particular bit to correspond to a particular pin. Oftentimes, these pins are multiplexed with other functionality. So they may have pins. They may say you can either use it as a GPIO or you can use it as something else. So very powerful and a big friend of yours. And in a typical MCU, like the one we played with last Friday, a large number of pins are dedicated to this. So I've given you the example of Raspberry Pi out here. So Raspberry Pi, this is a Pi 0 wireless specifically. So there is a header out here and a whole bunch of pins out here. Some of them are dedicated for programming, right? But many of them are just general purpose I/O pins. They're labeled like GPIO1, GPIO2. The reason they're called general purpose is because they really don't have any pre-assigned purpose. You get to use it for whatever suits your fancy. There are lots of interesting usages for it. Firstly, most like the hello world of standard programming is to blink the LED, right? I mean, your platform is up and running. I don't know if you guys noticed last time when you got that embed, the very first time around, it had the blue LED blinking because that was my test application that I just to make sure that the platform was up and running. Usually these GPIOs, you can hook up an LED to it along with a resistor, or perhaps even without a resistor. So LED is rightly matched, and then you're good to go. So very easily done. Usually these pins are designed to provide sufficient current that you can do meaningful stuff with it, but not a whole lot of current. So if you are hooking it up to something which will draw a lot of current, then you will need to put some additional amplification. Very widely used to control external peripherals. In particular, you can use it to control a relay. What is a relay? Switch. So what does it do? So it's a switch. You're right. So a relay, let's go back out here. A relay is nothing but a switch, and the idea is that in the main part of the thing we have some sort of a high current, and its control, I want to do it with minimal current. So the control part is what I will hook up to the GPIO, and the main part will be connected to high current or high voltage. So like for example, it could be controlling your pool motor, which is 240 volt AC actually. So it could be either high voltage or high current, and then your little device may be connected to this guy, like your Arduino or whatever. Now, doing this would actually be fairly risky. Why? Why would it be a bad idea for me to control pool motor voltage out here and my little GPIO sitting out here? You should never have high voltage, low voltage coming next to each other. Short, or you can get electrocuted. Okay. So what do we do? When you want to separate things out, high voltage, low voltage, what do we use for that? Yeah, what kind of resistors? What's this? Most transistors are most right. You need to isolate, right? You want to prevent high voltage from crossing over. Perhaps the best way of doing it is optical isolation. Okay, that is you. So again, going back, um, you put an isolator right here. Okay, so this is high voltage, and this side is low voltage, and you don't want them to be mixed with each other. So what optical isolation does is it uses phototransistor, so that on the left hand side you are going to be driving an LED, and its optical output is going to turn on off the transistor, and the high voltage cannot jump that way. There are other ways of making this thing happen, but if in your project you venture into things where you're controlling something which is high current, let's say something to do with home automation and all, then either get a relay which already has the isolation in it, or make sure you provide the isolation. Okay? Very important to keep the two separate, because you don't want to get electrocuted. Other ways of doing isolation, transformers, because you basically have two decoupled things. There is no connection between them. There is air gap between the two coils, and you can imagine other ways. Okay, with that digression, coming back out here, I can control external relays, and just generally motors and things like that. Software controls serial protocols via bit banging. Bit banging refers to software which just twiddles those pins in some creative manner, and in particular, I can fake various kind of serial protocols, which we'll see shortly. But like, let's say, serial USB protocol, things like that. But since you're doing it in software, it may be quite slow. But you could do it pretty useful. And finally, and the reason I want to bring it out, it's a huge aid for debugging. So, for example, you could, let's say your code is not running, okay? Well, at selective places, you can put some code there for it to twiddle a pin, and then you can observe that pin using another piece of hardware or an instrument, so that you can know whether your program is running. Like, for example, was my interrupt service routine firing? Was this routine running? How much time is this routine taking? Right? All of those things. It's in a standard computer, you have debuggers and all where you can kind of pause and look at things and all. Here, you could do that, but a lot easier is simply put these cheap GPIO instructions at the right places and monitor the pins. Put it onto a scope, put it onto a logic analyzer, or even use a second embed to just monitor the first embed, right? Because you can look at using the GPIO on the second embed, you can kind of create your own fake instrument for this purpose. So if you get adept at using GPIO, both reading and writing, it can make your life a lot easier than otherwise. Because one of the things, unfortunately, most of people who are working with embedded systems do not have access to is fancy test equipment. They exist, and in companies who are into huge multi-million-dollar products and all, like if you're working at Amazon or Apple or whatnot, you'll probably have access to those things. But in a typical academic setting, and frankly in most startups and all, you will not have that. So you have to become creative and use GPIOs as your friends, okay, to simplify your life. So you can use them for debugging, and in a sense, you can monitor the state of the GPIO pins by using standard lab instruments, or perhaps even another embedded system. You can use a second little embed to help monitor kind of your main device. So that's GPIO, very commonly used. A close cousin of these are the so-called analog IO pins. And most MCUs will offer some of them. Sometimes they may only offer analog in. Sometimes they may offer both analog in and analog out. It's relatively rare to see analog out but not analog in. So they are the outer part of GPIO. Again, very lightweight. But when you are dealing with analog, inside obviously everything is digital. So you need some way of going between analog to digital and digital to analog. And guess what? Those things are called analog to digital converter or ADC and digital to analog converter or DAC. Again, you would, if you go and do some circuit course, any one of you have encountered ADC and DAC in any courses? No. Okay. These are pretty challenging to design, okay, and if you enjoy taking analog courses, Razavi or Kamati or Abhidi, then they teach all sort of advanced courses in this thing, and you can, yeah, I guess they're hard, right? I mean, so most of us don't take it, right? You can think of them as black boxes. So main thing is that ADC takes an analog signal input, okay, with respect to a ground, and gives out the binary output. So inside the MCU, this would be the pin. So this would be your pin in the MCU. So this is an AI pin. Okay. And what will happen is there will be some instruction which will say, go read that pin, and then this ADC will trigger and it will get this binary output. Now this is a gross generalization of pretty complicated circuit magic that happens inside, because going from analog to digital means I have to sample the voltage, then I have to do some sort of a conversion, figure out what's the corresponding binary number. All of that is fairly complicated, which is why people devote their entire PhD thesis studies designing better and better ADCs. In particular, ADCs which can give you lots of bits, and ADCs which can do this operation at a high rate are very hard to have. So just to give you perspective, let's say you are monitoring something very subtle, very sensitive, I don't know, like vibrations of earth, the seismometer. You may need 20 bits, 22 bits. Just to put in perspective, 20 bits is 1 part in a billion, something like that, right? So very, very tiny signals that you are trying to transmit. Rate is another part. There are phenomena which change very rapidly, and therefore you need to be able to sample them very rapidly. And again, making fast ADC is pretty hard. So if you need fewer bits and you need to sample slowly, like I don't know, it's a temperature, it's pretty slow. On the other hand, if it's acceleration of human body, you need to perhaps monitor it into kilohertz. And then heart signal, again, these things tend to be in kilohertz. And then there are phenomena which are even more rapid. So rate and resolution. Those are the two things. Okay, I already have them. Okay. Bit resolution and sampling rate. Sampling can be either periodic or aperiodic. Okay. I'm going to talk about this later in the course, but one of the most beautiful result in all of information sciences is the so-called Shannon sampling rate or Nyquist sampling rate theorem. Okay, so many of you will have seen it. What it loosely speaking says is the following, and I'm going to write it down. Okay. What it says is that if we sample an analog signal at a rate which is greater than equal to 2 times the highest frequency it has, okay, then we can perfectly reconstruct the analog waveform from the samples. Okay, and so what it means is that let's say I'm monitoring temperature, and the highest frequency component of the temperature, if you were to take it Fourier transform and look at what the frequency component is, if it is, let's say, it changes like 1 hertz, let's say, then sampling at 2 hertz would allow me to do perfect reconstruction. A couple of caveats out there. Firstly, my samples have to be very precise, right? They have to be real numbers. But of course, we don't have that. So we are losing in this picture. We are assuming in this case that we somehow have infinite precision, but we don't, and therefore there will be precision loss because of that. Second thing is, what happens if there was actually signal at higher than this frequency? That is, I was wrong. If f max was not actually the max, and there was even a higher frequency available, then truly bad things happen. So what, in a way, happens is the following. Let's say I look at my signal, and let's say it has some spectra. If I look at it, a spectrum of it, then this is supposedly my f max. When I sample it, then essentially, if this is my sampling frequency, and if I look at the signal after sampling, it's as if spectra is repeated again and again. Very important is this fs is more than 2f max, so there is no overlap out here. If this is not true, then these spectra bump into each other. They overlap, and then you cannot recover. Okay, so before you sample and before you decide the sampling frequency, it's very important to ensure. So from a designer perspective, you have to ensure fs is greater than 2f max. Or equivalently, you have to ensure that f max is less than equal to fs over 2. So I have to make sure that my signal that I'm sampling does not have any frequency components higher than half the sampling rate. How do we ensure that? Use filters. So you put some filtering circuitry to remove any frequency components which are higher than half of the sampling frequency. If you don't, then you have irretrievably lost the ability to reconstruct. And you can create these, I mean, there are filter chips and all you can buy if you've done some circuit design course, which hopefully you would have because there are some lower degree courses using op amps and resistors and capacitors. You can design filters and create these. But very important that you sample them. Now, fortunately, your wires themselves have some resistance capacitance. The inputs of the pin themselves have some capacitance and resistance. So there's some natural filtering effect that in any case happens. But it doesn't, and sometimes these chips, MCUs themselves, would have some filtering going on. So you can often get away without it. But in a good system design, you should certainly do that. So that's the analog input side. One other thing that happens is that oftentimes this ADC is very expensive, okay, because it has to do a lot of stuff in it. But I may want to sample multiple analog signals. So very common is to multiplex them. So what you may see is multiple pins, and they feed into the same ADC. So this bottom one is actually for the Hexaware MCU, and what you see out here is it has actually 4 AI pins. 1, 2, 3, and a fourth one for which the circuit blow up is shown. And you see the set of switches out here. So the idea is that through software or some hardware, we very rapidly cycle through this thing. So for a while, we'll take one sample from pin 1, then from pin 2, then from pin 3, then from 4, and then cycle back. And we're using the same ADC. Of course, the effect of this is that if I am sampling multiple pins, then the rate for any given pin has to be lower. So if my ADC had a rate of 1 megasample, and if I'm sampling only one pin, I can sample at 1 megasample. If I'm sampling all 4, then max I can go is 250. Again, these details you will only get to know when you actually look at the processor memory. But this is very common because it's very expensive to have ADC, multiple ADCs, one per pin. So this is a very common strategy that is used, namely having multiple AI pins feeding the same ADC. Then you also have AO pins, analog output pins. Those are DACs. And in that case, you are going to write some binary value to the register, and the output is going to be an analog signal. And again, you are going to do it repeatedly to fake whatever waveform you want. And then there is some smoothing which is done on the output side. So you can kind of generate sine waves and other waveforms that you want by either updating things periodically or asynchronously as you feel like. Now, with DACs, it's hard, you cannot multiplex, right? Because they are driving an analog signal output. So if I have 2 digital analog output pins, then I will need 2 DACs. And that's why you will typically see that the number of DACs available is very few. Like you may see MCUs that will give you 6 or 8 or 12 analog input pins, but they will usually have 1 or 2 output pins. And the reason is I can't do the multiplexing anymore. I need 1 DAC per thing. And by the way DACs are designed is very similar to ADCs. Oftentimes it's actually done using an ADC. So no multiplexing. Yeah. Okay. So they are expensive to have. You need 1 per pin. And they don't let you. So I think our particular processor in Hexaware, if I recall right, it has 2 DACs. Sorry, two digital, 2 analog output pins, and it has 4 analog input pins, and it has some other stuff. So that's the story on analog. So you have now 2 classes of general purpose I/O, right? General purpose digital I/O and general purpose analog I/O. Then we have, this is the analog part. So it has 16-bit ADC, up to 2 of them, depending upon the precise processor model. It has 12-bit DAC, again up to 2 of them, and it has a second type of ADC. It also has some analog compatibility, so some other stuff in it, but for our purposes, we have up to 2 16-bit ADCs, up to 2 3 analog comparators, and 2 12-bit DACs. So that's the analog side of the story. Next thing is the following: is it a cheaper way of getting analog out? Now, remember, our digital pins are much simpler, right? I mean, we just read and we just send something out. So, is there a cheaper way of conveying analog information as opposed to actually sending out waveforms, right? So, just on the output side. So, very often what happens is we want to control voltage on a motor or voltage on a LED light bulb, these kind of things. So one way you could certainly do it is to use a DAC, but like I said, DACs are pretty expensive because I need all that circuitry behind the pin, and oftentimes MCUs may not even have a DAC. So can I fake analog output without having a DAC? So people found long ago that there is an alternative way to do analog using digital, and that's called pulse width modulation. And the concept is the following. Let's say I look at a digital waveform. It's just going between 2 voltages, 0 volts and 60 volts. This waveform is 0 half the time and 1, so it's a 0 volt half the time, and let's say 3 volt half the time. So it has what we will call as a 50% duty cycle. Now, if I were to look at it, if I were to smooth it out, if I were to think of it, what is its DC voltage? If I were to look at the spectrum and I were to see what is the zero frequency component, then that's essentially taking the average of it. And the average of it would therefore be, so it's a 50% duty cycle, it would be 0.5 times the maximum voltage. And I can play the same game with energy and other 75% duty cycle. Now the average voltage becomes 0.75 times 25% duty cycle. So as you can see, duty cycle, namely the ratio of 1 to the whole period, lets me control the average voltage. And PWM exploits that insight. It basically says, if I could get the other side to simply average things out, then I can convey the voltage, the analog value that we want, by changing this duty cycle. And that you can do through software, right? I mean, I can decide when to make the signal go 1 and when the signal go down to 0 by playing timing games within the software. I can do it very precisely using the timer hardware that already exists. So that's kind of the basic insight. So it's the way it gets used. Let's say I'm trying to control a motor, a DC motor. Then if I what I want to do is that I want to give it a signal. So if it is the signal is continuously high, then the motor will run full speed, and at different other values it will change the speed proportionally. It turns out that this way of talking to motors to control its speed or even to control its position, in case of motors the position is controllable, has become very common, that you can buy so-called servo motors for robotics and all, which take a PWM signal. Okay, so you just need to supply a PWM signal, and the motor comes with the circuitry to handle kind of rest of the stuff. They are often called as electronic speed controllers. So motor plus a little circuitry. So if you are into remote control cars or drones and stuff like that, you'll find that the motors used in them basically come with these kind of controllers, and they basically take up PWM signal. And hopefully you would agree that generating these waveforms from software is quite trivial. So the magic that happens on the other side, inside on the motor end of things, is the following: that the motor, or it could be your LED light bulb, it's hooked up in what is called as an H bridge. So, and what it is the following: the actual voltage that the motor works at, it might be 12 volt, 24 volt, and the ground. And we have 4 switches. So the switch on the left here, switch on the right and top, switch at the bottom left, bottom right. And what we do is that we basically turn on off these switches according to the state of the PWM signal. Okay, and then we control the direction of the motor by whether it's a top left and bottom right, or whether it's top right and bottom left. So we can change the direction in which the voltage is applied. In case of LEDs, the reverse direction will make sense. But by rapidly switching, these switches are on and off, I can basically make the current flow through the motor in the right direction for the right amount of right fraction of time. And the motor internally has inductors, and also they take care of all the smoothing filtering that you want to do. Right? Remember, motor itself has a mass, and therefore, even when I remove the voltage, it still keeps spinning, right? I mean, so it naturally has a damping effect on the signal. So I basically just make sure I'm supplying it the right amount of energy, and it takes care of it. So what you find in these motors and LEDs, which are dealing with LEDs and all, is basically inside they have this bridge, and then from your MCU, you just need to convert the PWM system. And this is essentially kind of a standard that kind of exists. There's a reverse standard also that exists. And let me, so remember, with motors, I want to control its speed, but perhaps I also want to measure its speed. Same story. How do I measure its speed? How can I measure how do I convey the speed? So again, PWM comes to the rescue, and let me show you how it is done. Actually, yeah, maybe I'll resort to a website. Give me a sec. So this is what happens here. On the same spindle as the motor, there's a disc. And on the disc, there are holes around the periphery. And there's an LED and a receiver which is positioned just right. And then you rotate, when the motor is rotating, then the waveform that will come out here, its frequency will correspond to the frequency at which the motor is rotating. And I can measure these things. So it's not PWM, but it's pulse frequency modulation instead of bit modulation, but same concept. So what comes out of the motor in form of the speed is actually this kind of a waveform. And now in the reverse direction, using your timers and the MCU, you can measure the speed of the motor. And by the way, similar concepts apply for, you can get the direction by having two slightly, two sets of holes which are appropriately positioned so that you can compare the phase of these two digital signals, which one is leading, which one is lagging, and then you can figure out the direction of the motor. So very cheaply, by having just a single wire come out of the motor or two wires come out of the motor, you can have the motor convey a real number, the speed out. Now, it's not really a real number because your resolution is going to be decided by the resolution of the timers that you're going to use to measure it, as well as what is happening to these slips out here. Okay, so there are resolution limits nevertheless, but it's a very cheap way of conveying analog information out of a motor or such devices and sending analog information to the motor or to a light bulb. And in that case, you don't need analog input and analog output. You're basically using PWM signal. You're making use of the timing properties of the signal to do the analog to digital or digital to analog conversion. So very commonly done, something that good to be familiar with. Not the resolution is limited, so it's fine for motors and light bulbs and all, but it's not going to be good for very sensitive sensors and all. But a lot of stuff in daily life is works perfectly fine. So unless you are in some super fine position control or speed control, like typical robotics motors, you'll see that this is called speed encoders. Okay. And likewise these dimmable LEDs and all, same thing. You don't need a whole bunch of, I mean, you're good to go here for, let's say, 10 bits, 12 bits, 16 bits kind of thing. If you need something very sensitive, then you are. And of course, it doesn't really work for everything, right? I mean, if I'm measuring some physiological signal from the human body, let's say the voltage in the brain or things like that, then obviously this doesn't work. Then you are back to using regular ADC. But for a lot of things, this does work. Okay, so that was PWM. Let's do the following. Let's take a 5-minute break, and then I want to move to more specialized forms of I/O. Okay, how they are handled. So 5 minutes. Okay, let's start. So we saw these IO pins, which are uh, meant for more general purpose digital and analog interfacing with the outside world. But then you'll find that if you look at kind of the MCU, they typically tend to have a lot of other pins also. And what are they about? So generally speaking, these are uh, standards that have emerged for specific ways to talk to peripherals. And they've often been pushed by different companies and they have kind of become de facto standards. And also, in some cases, they may not be standards, but they're so widely used. PWM is a great example that oftentimes MCUs provide them. So you'll see, I don't know about our specific MCU, but many MCUs have PWM hardware built in, and they will just let you write duty cycle ratio, and it will take care of the rest. And likewise, there might be hardware to do the encoding signal, the speed encoding that I mentioned, that you just tell it and it will just give you the number and it takes care of all the timing details and all. So that's it. But when we generally look at the kind of things that you'll find, there's various dimensions in which sort of these things end up differing, and kind of these different standards or different ways of communicating. What kind of data rates, in case of radios, what kind of distances they are designed for, wired versus wireless, is the data communication serial or parallel? I mean, the wired versus wireless again. Let me speak. Okay, but all those kind of stuff. So just to give you some example, on the wired side, you will find firstly our good old friend USB, and then also UART, which I guess normally we just think of as the serial port. If you have an older computer, it may still have a serial port in it, but modern computers don't. SPI, I2C, these are much more common on the embedded side. Parallel, you have PCI and PCI Express and compact PCI. Your laptop still has either PCI Express or something like that. And then there are things for communicating with distinct systems like Ethernet, which is actually that little embed we played with on Friday has it. CAN is Control Area Networking Bus. It's used in cars actually for a bit. If you have a and most cars currently have CAN bus internally. Some European cars don't, and then many a times nowadays MCUs also have radios built in because wireless ways of talking with other peripherals and other nodes have become very common. Bluetooth or Bluetooth with low energy mode, and this is a radio which you will find quite a bit in fitness kind of stuff. It has been overtaken by BLE, but still older exercise machines and all often have. And Wi-Fi Direct is a particular mode of Wi-Fi to talk. You have two devices talk to each other directly. So like your iPhone has Wi-Fi Direct. A2.15.4 or Zigbee. This is used by a lot of these smart light bulbs. It's a radio standard so that devices can talk to each other and they can hop. Like A can talk to B, B can talk to C. They kind of form a mesh network. Okay, so this is a mesh. And then Z-Wave is a very similar thing. It's a proprietary thing, and you will find that again in light bulbs and light switches and stuff like that. So again, what happens is since these are very commonly available, so oftentimes MCUs may have support for this. Like for example, a company called Texas Instruments and a couple of other companies, they make a lot of MCUs where 80.15.4 radio is built in. In fact, if my recollection is right, the second MCU on Hexaware, not only does it have BLE, it actually also has 81.15.4. So it's very, very, very common. Then there are things for medium or long distance communication. Wi-Fi is certainly there. LTE is your good old cellular. So for example, Qualcomm makes chips where the processor and LTE modem all on a single chip, and oftentimes they are used in things like these vending machines and all, right? Because or stuff you see in like those little displays in cabs for payment stations and all. They often use these chips where cellular radio is built in and they kind of just talk. LTE Direct is a version of cellular thing which is meant for phones to talk to each other. So without going to a base station. Again, there are chips with support it. LoRa is just long range. It's actually a version of 802.4 which is designed for like city scale communication. So you can have sensors all over the city and then talking to something that's on top of Wi-Fi hall. Again, you can find tiny little boards like Hexaware with the LoRa radio built into it. So these are some of the common things that are out there. What I want to do is to go into a few of these to get some underlying concepts across, and also so that you know their existence and how to talk to them and use them. Hexaware MCU has a lot of these things, and in fact, on the breakout board, many of these things come out as well. So let's dive into it. So first question is parallel versus serial, right? I mean, so parallel bus means that I have multiple data lines going out, and when I'm conveying a piece of data, I send out its various bits in parallel over different wires. And in serial, I send out the bits one after another on, let's say, a different clock cycle. Okay, so some sort of a clock signal, and every time the clock changes, I push out a different bit. Okay? Question for you: which one is better? Okay, so this is parsimonious in pins. So that's a plus. I guess counter of that is I have more pins here. Okay, so which one is faster? Huh? Okay, so parallel has more pins. So at the same clock rate, parallel would be faster, right? More pins. So question really becomes, can the clock rate always be faster? Because could it be that I cannot make the clock rate faster? Okay, so I can say faster for same clock rate. Question is, which one will have a faster clock rate? Anyone? Serial. Why? Yeah. Okay. So the issues have to, it falls under distance. Okay, and the issue is the following. Let's say I'm sending all the bits in parallel out here, and I'm sending it over a long distance. Then each one of these wires, if they are even slightly different length, I may send them out at the same time, but they may arrive at the other end quite staggered, right? Because if even there is a, I mean, just think of it this way, uh, 1 nanosecond speed of light is around a foot, right? I mean, speed of light is 3 × 10⁸ meters, so that means roughly 10⁹ feet, and so yeah, so 1 nanosecond is 1 foot. So roughly a nanosecond, 1 foot. So if I'm going long distances and if I have discrepancies creeping in, then I begin to have the data arriving in a static manner, and things can be worse very rapidly. So here I have to make sure on the receiving side, the difference in the delays that happen is still within my clock period. So at very high rates, I will run into problems. So if I have cabling going through chassis, and if I have long pressures on the PC board and all, then I can run into trouble. On the other hand, if everything is inside a chip, this is probably fine. So if I want to get into really high rate, serial offers a simpler path out, because I basically don't have to worry about synchronization across bits. Actually, the same challenge also happens. Should I, here I have shown clock signal being carried separately, but I may also have skew between clock and data. So like here I'm showing these different bits are going precisely at the clock edge. But if these are two separate wires, by the time they reach on the other side, maybe they are dissimilar. And so I can't just use this clock signal on the other side. So in fact, even better is for me to not send a clock signal, because that is asking for trouble. So serial lines where, and the other party somehow just recover the clock signal, right? So very rapidly you get into very complicated stuff. Professor Ken Yang group, for example, out here does a lot of work on high-speed serial interfaces and all. But generally speaking, you would notice that a lot of the high-rate interfaces that have come out in recent years are all serial, right? Your USB 3C and all, these are all serial interfaces, okay? Because parallel tends to be kind of complicated. In fact, the parallel port in your PC, which if you go back 10, 15 years, there used to be a parallel port and the printers used to connect to it. They have disappeared. Okay, most of you are too young to ever encounter a serial in old PC. Look at it, there is a parallel port in it. Okay, and it's gone dead. Okay, so going back out here, I think within a chip, parallel is obviously fine, but going out, between the fact that I can push higher speed as well as so much more parsimonious on the pin side, that serial is winning. So you would not find parallel interfaces on MCUs. So this is kind of dead. Okay, so now let's look at the serial interface protocols. So why serial? We talked about low pin count, avoid timing issues, but may need clock recovery. I talked about that it's perhaps a good idea to not even send a clock, but then I have to figure out the clock from the other side. Like you're sending me the bits, what rate are you sending me? What was your clock frequency so that I can look at the signal at the right time? It's also difficult to memory map. What I mean by that is if parallel was coming in, then I can just think of it as if it's a memory location I'm reading from it. For serial, I need to first convert it into parallel before my software can do that. So some more complications there, but still. So some of the jargon that you would see across serial interfaces, synchronous versus asynchronous. Synchronous means there is a clock signal, and I can, at the clock signal, I can look at the data value. Asynchronous means there is no clock signal. Okay. So full duplex. Yeah.
These clock signals aren't actually exactly square.
You mean 50% duty cycle?
Yeah, in general, like any clock cycle in any microcontroller, I mean, they are due to non-linearity, suppose
Yeah, a real clock cycle will look something like firstly there will be some transition, and then the low and high time.
did they like in the initial stages of developing serial, did they face any issues like sending out data because of
So a real clock signal will typically look something like this. So there will be some voltage transition time, and then the high and low time are not necessarily equal. Okay.
did they while developing the initial stages of the serial interface, did they face any issues synchronizing visual?
So I think firstly one reason to not send a separate clock is you save one line also. Okay, besides the fact that you don't run into synchronization issues. So clock recovery, which basically means that just looking at the data, can I learn what the frequency was? Which you can, right? I mean, by examining when the data transition was taking place, you can have something to do it. So those things went out. So most serial protocols, that the common one that you encounter, the so-called the RS-232 serial port, there is no clock signal. But many serial protocols do have a clock signal. So it depends. If you send a clock signal, then the life is easier for the other party, right? Because it doesn't need to recover the clock. But it does mean that you can only go short distances.
Could you explain how come in parallel? How would it be?
Well, yeah, so like a parallel port, for example, you see, it used to be just sitting at a particular address and I would just go and read it. Whereas for the serial one, you would need to have some hardware which takes those serial things coming in and maps it into a parallel one. Okay, alternatively, you could imagine I read only bit at a time and then in software I convert it into a corresponding parallel number. But that will be very clumsy. So remember, I want to write an 8-bit character to a peripheral. So some hardware has to take that parallel thing and convert it into serial, and some other hardware has to do the reverse. Okay? So it just needs some more information. Okay, so clock is one thing. Full duplex versus half duplex. Whether I can simultaneously send and receive the data, or whether at any given point in time data has to go one way or the other. Again, these different ones differ. Master slave. Many of these things have an explicit notion of one device, typically your MCU, being the master, and all the peripherals being slaves. So communication is initiated and controlled by the master device. Usually, if it is such systems which have a single master, they are often synchronous, and the master also supplies the clock. Okay, so if there is a single master, then typically that single master will supply the clock, and that clock will be used for data transmission in both the directions. So the slaves can be made super simple and dumb. That's kind of the idea. Then there are buses which are multi-master. We'll see examples of these, but so multi-master are things where you may have multiple MCUs connected together and multiple peripherals, and sometimes MCU A is talking to peripheral 1, sometimes MCU B is talking to peripheral 1, and somehow sort of clearly for this thing to work with multiple masters, there has to be some arbitration scheme, right? Because multiple masters, we have to decide which one gets to use that communication medium. This becomes important because oftentimes we do have multiple MCUs sharing a peripheral. Right? So some arbitration is needed. That CAN bus that I had mentioned, which is used in vehicles, is an example of it. There are many computers in a modern car. In fact, a modern car, even low-end ones, have close to 100 different MCUs, and they are talking to each other and sharing that one CAN bus. So all this magic has to take place out there. And finally, some other terms that you would see: point-to-point or peer interfaces. In this case, no one is the master, no one is a slave, everyone is equal. So socialism, multi-drop, one transmitter, several receivers, and multi-point, more than two transceivers. So these are all jargons you would kind of see, less important, so glossing over them. But across the spectrum of various serial interface standards that exist, and you will find many of them on your MCU, you'll see kind of these kind of terminology being used. Perhaps the most common one and most widely used is the so-called RS-232, and behind that what is called as UART, or sometimes it's called USART, USART, Universal Asynchronous Receive Transmit. Okay? And RS-232 is UART with a specific voltage level. Okay, so this RS-232 is basically defining additional voltage level. So it's a very common serial interface that you will encounter on all sort of peripherals, and almost any MCU out there will support it. It also used to be available as an explicit port on your computers, but lately it has disappeared because USB does this and more. But in the embedded arena, it is still very much there. It's basically a bus which is capable of full duplex communication between a pair of transmitter receiver. Okay, so two entities either can send or receive. Speeds greater than 115 kilobits per second. Actually, the standard only specifies some low speed, but it's almost universal that you will find speeds maybe up to even 384 or even excess of a megabit per second available. All depends upon the distance. So usually you will use them for short range things, but with appropriately shielded cable and all, you can go hundreds of feet. But then very good cabling and also lower data rates. So a typical connection looks something like this. There is a shared ground, and then receiver of one connects to transmitter of the other, and receiver of the other, so basically three wires. Okay. There are possibilities of some additional wires so that you can do what is called as flow control, where, for example, if one party is sending bits at a very rapid rate and the other one is not able to process, then it will say, hey, slow down, stop. And so there are a couple of additional signals that can do that, but you don't need to use them. It's very uncommon to use them. So this is the most common configuration. And then what happens is when we send the data out, it is sent out, again, remember serially, this is on one side, one wire. There is a start bit and a bunch of data bits and then a parity bit. What is a parity bit, anyone? And then finally a stop bit. What is parity? Yeah, how does it work? What is parity of a number? Yeah, so what is... So parity of a binary number is either 0 or 1, and that basically defines whether the number of ones is an even or odd. Okay, so if the number of ones is even, then it's 0 parity. If number of ones is odd, then it is 1 parity 1. And the idea is, once you add the parity bit, then the resulting thing will always have even number of ones, right? Because if it was odd, then its parity is 1, so I add a 1 as a parity bit. So it basically acts as a very poor but often sufficient error. Okay. So what goes on out here is, so if you see on this yellow line, there is a start bit, so which basically is indicated by a particular combination. Then there are a bunch of data bits, and it could happen that I have two successive 0 bits or two successive 1 bits. So for example, here you see two successive 0 bits are going, so it's 0, 0, and here you see 1 and 1, so successive bits are going through. And then at the end, I need to have a parity bit, so that's parity, okay. And then finally the stop bit, okay. Sorry, nope, I got it wrong. Yeah, this one actually corresponds to no parity. Okay, so in this one there is no parity, and then 3 is the stop bit, and then 4 is the start. The next one is start of next bit. Okay, so the standard allows all these things. You can have parity bit, you may not have parity bit. How many data bits do you have? All these things are configurable. So in this particular case, this is one start bit, 8 data bits, and no parity bit and stop bit. If you open a terminal program, you can usually configure these things. So let me show you, for example, I use CoolTerm, which is similar to PuTTY and these kind of things. And then you can configure these things, right? What is the baud rate? What is the data bit? It allows you different number of things. What is the parity? What is the stop bit? And then the CTS, DTR, and XON, these are those other wires, which I said are mostly not present. So you can kind of ignore them there. So basically, your serial port can be configured accordingly. Mbed uses something, and usually I think this 8 no parity and one stop bit works fine. But if you're unable to communicate, then that means you probably have these settings incorrect. Okay? So you need to make sure the settings are correct. Almost any microcontroller will include support for this. It is usually referred to as UART, but sometimes it is also called as USART, in which case S stands for synchronous. So it's in this case it's universal, synchronous, and asynchronous. What happens in USRT is that there is also a clock line possibly, and you can do even higher data rate transmission in a synchronous mode, but over short distances. Uh, so in your processor, you can check whether you UART or whether you have USRT. So that's very commonly there. And the other part I want to mention is that your chips, MCU chips and all, they are designed to work at low voltages, 3.3 volt, 5 volt, and 1.8 volt. These are common voltages that you will find for MCUs. RS-232, which is the standard, is designed for communication over long distances. And it represents zeros and ones differently. Logic 1 is represented by a negative voltage anywhere from -3 to -25 volt. And logic 0 is presented by voltages between 3 and 25 volts. So you can see the voltages can be very high. And the idea is that RS-232 is made for long distances, over cabling. So firstly, you don't need to use RS-232 voltages. You can stick with the voltages that you have on your MCU and on your peripheral, and as long as they're compatible, you're fine. But if you are connecting to something which is RS-232, then you better be prepared to handle this larger voltage, and therefore you will need a voltage conversion in that case. So for example, if you have an MCU, two mbeds talking to each other, for example, they have both have UARTs, they're both operating at whatever 3.3 volt, you can just hook them up, no problems. On the other hand, if you get some peripheral device that says RS-232, then to connect your mbed to it, you would need a voltage converter. Okay? That's not built into mbed. That will be a separate higher voltage chip that we will have to do. So it's relatively uncommon to deal with higher voltage RS-232 unless you are connecting to some sort of system, its own box or something like that. Most of the time, you'll be dealing with just regular voltage. So MCUs and all is just standard. But so you don't have to use these RS-232 levels, but be aware that if you are working with not a UART, not just a UART, but with RS-232, then you better make sure that you have the right voltage. The other thing to notice is that things are, the positive is positive, logic 1 is negative voltage. Okay? So just something to be aware of. So this shows how UART communication for a letter W looks like. So firstly, we take the ASCII code for W. Normally the line is just idling at a high voltage. We send a start bit, which goes low. Then I'm sending the data bits. In this case, we're sending 7 data bits because ASCII code is 7 bits. So we're transmitting 7 data bits. Least significant bit first. Then we're sending an odd parity bit. And then we're sending a stop bit. And then finally again the line bits. So this is all that is going out. And remember, these are two separate systems. They don't have a common clock, right? So the receiver from this signal has to figure out how to sample. Now, first thing we can do is we can tell the transmitter and the receiver what the baud rates are. And they can set the baud rates according to their local clocks, right? And if we assume that the clocks are reasonably accurate, we are done. So for UARTs, that typically works fine, which is why in that cool term we had the baud rate, 9600 baud. So that is basically telling it what rate to sample. It still has to figure out when to sample, and that it will do by looking at the edge. So this hardware or software on the receiver is continually monitoring this. When it sees the line go low, it says, aha, that's the edge, and then it will start sampling at a particular rate. If you want to be really accurate about it and say, look, it's possible that my clock is not entirely right, then you are perhaps going to also measure the gap somehow, but that's not possible because this is 0 and the first bit is 0, I'll not even see the edge. Okay, so usually for UART, it's not the case that you work this way, but for other serial standards, instead of a simple start bit, we have a pattern. And that pattern will have multiple 0 and 1 transitions so that you can actually figure out what the sender's frequency was and then adjust your clock. But the UART, you don't need to do that. So, your goal is that you would like to sample the bits right in the middle, right? So that's the safest point to have. Maybe you might even want to sample it a couple of times or 3 times and do some majority voting just to guard against error. If the receiver samples too quickly, then by the time you are reaching the end, you will be sampling the wrong thing. Because, like, for example, if you see what's happening is in this case, it's sampling it twice out here. Okay, so it's getting it incorrect. So you have to make sure that you are sampling it just at the right rate. Okay, very important. In cases where you're again remember there are 2 different clocks involved here. Receiver has its own oscillator, transmitter has its own oscillator. If they are misaligned, bad things can happen. So usually the standard also requires that your clocks be good enough, your oscillators be good enough to work. If I do it too slowly, then I may miss things entirely. So for example, missing something here. Well, I guess this one we are missing out. So if you look at this one, this is not getting sampled at all. Okay, so then you run into problems. So it's very important to get kind of the alignment and the frequency kind of right. So that was UART. Super simple. You can do the bit banging approach to it also, as in use if you have more UART devices to connect to than the ports on your MCU, then in a pinch you can fake a UART in software and just use some GPIO pins for GPIO pins together with timers. So UART very commonly used. Next one is I2C. We are running out of time, so I'm just going to quickly introduce it and then pick it up next time. So I2C stands for Inter-Integrated Circuit Bus. As the name implies, it's meant for chips to talk to each other. It was originally done by Philips Corporation, which is a European company. It is a half duplex synchronous, so no longer asynchronous, there's a clock signal here, multi-master bus, which works with 2 signal values, two signal wires. So there is a data line SDA, and then there is a clock line SCA. And moreover, these lines are pulled up by a resistor to do what is called a wired ANDing. So in the remaining few seconds, I just want to describe what wired ending is so that next time that we talk. So the idea out here is the following. We have transistors. Think of transistor as a switch. If the switch is on, I connect the wire down to ground. So I pull it low, so the wire gets pulled low to 0. Now normally, our circuits have also a similar switch up here, which pulls it up to 5 volt or 3 volt. So when I want to put a 1, then the upper switch is on, the output wire gets pulled up to 1. So this wire, so we're focusing on this wire, okay? So normally, to output a 1, there will be a switch at the top, which will be driving it to 1, and the bottom switch will be off. And if I want to put a 0 out here, it's the other way around. The upper switch will be off, and the bottom switch is pulled down. But in I2C and circuitry like this, there is no upper switch. All we have is a bottom switch, and it's either on or off. Now, if it is on, it's pulling it down to ground. But if it is off, then the wire is kind of floating. Now, of course, that would be bad. So what we do is we put a resistor out here, a permanent resistor, tying it to ground. So now, if you think about it, what happens? Let's say I have these logic gates which I showed you, and let's say the bottom transistor and all of them was off. Right? What would happen to this wire? So again, bottom transistor is all these 3 logic gates that I have shown. These are logic gates. Okay, so I realize some of you have not done. Think of these. These are 3 different pieces of circuitry. Okay, and let's say the bottom transistor and all of them was off. So each one of these things is nothing connected to the ground. So what will happen to this? What's the voltage?
Good question. Which kind of transistor?
Doesn't matter. Bipolar, MOSFET. Off meaning disconnected. Transistor is turned off. Okay. So going back out here, the voltage is, let's say the voltage here is low, transistor is off, so the current cannot flow through. So it's as if these 3 guys are disconnected from the wire, right? So what will happen to the voltage? It's called a VCC, right? Because all happening is being just pulled up, right? So if all of these 3 were off, then this is pulled up. If even one of them is on, the downgoing transistor, then it will be pulled low, and therefore the voltage will become 0. Okay? Because I'll have, this is relatively high value resistance, so I have high value resistance, and essentially short circuit, so it will just be pulled down. Okay? And some current will flow through it, but since R is very high, so that current will be very low. This thing is called wired AND, because the effect is as if I'm doing an ANDing function, right? Because what it is saying is that if all of these 3 guys have their bottom going transistor off, then the output is high, right? So I want all of these 3 things to be outputting logic 1 notionally, so that I get a 1 output. So I'm without putting an AND gate, but I'm actually getting an AND gate effect. I'm getting an ANDing function. So I2C does this. So I2C requires that this SDA line, it should have a pull-up resistor like this. Okay, and actually so does the clock. They all have a pull-up resistor. And then the circuit driving these lines at each one of those chips looks like this. That is, it only has a pull-down transistor. There's nothing to pull it up. Okay, so kind of the idea is, if no one is driving those wires, then the wire is at 1 because it's being pulled up. And the moment a master wants to transmit, it brings it down. Okay, so that's how I2C circuit-wise is designed to work. Using this, they are able to accommodate multiple masters because at any given point in time, now one master has to can take over the bus and then transmit, can talk with its slave chips, and at another time a different master can do it. How that happens, we'll talk next time. But I2C is again extremely commonly used and a very versatile thing.